But don't give up you're getting there in pieces, or you feel someone's getting there ahead of you. Don't give up, because there's different things people have, different Achilles heels when you approach this material. Some people might be closer to doing the right things to learn it. It's what you do, and it's a skill. So everyone in here is able to get that, and I will make sure all of you get that. 100% of you will be able to do these things or think this way by the time the class is over. And I'll make sure that the grade also reflects that. So you kind of have to trust me as you're going along. So it's about how much you're learning and being able to do this. So that if you're met with this again, you're not going to fear it. You'll be like, I've done this before. All right, so the kind of math you need for this next section is 205 or 255, two of our favorite classes. I'm bringing it back. So the topic, these are called multivariate probability distributions. So what they are is, this is just an example that I took from the book. Your book is actually really good. It has a good mix of examples, and the theorems sometimes might be obtuse, like that phi sub p thing. The reason I picked that one is I thought it was kind of poorly written, but still we have to be able to read them. So they took a sample space of die tosses. They actually, I think, listed things out, but it's just you're looking at two die, throwing it out, and then you have this ordered pair. If you ever went to Colonel Watts for help, she'll tell you write this sample space out. This is math shorthand for writing the sample space out. It's a combination of first coordinate I, comma j, where I and j are both members from the set 1 through 6. Well, there's lots of random variables that you could have on this sample space. Can you think of one? Say again?
No. The sum of the two die.
Yeah, you could do the sum of the two die, whatever they landed on.
Event where die 1 is 5.
So that's an event. So random variable is a function where you input something from the sample space and the output is a real valued number.
So number of dice that get a 5?
Say it one more time.
Number of dies that result in 5?
Yeah, you could do something like that.
It's like any sum or product.
So I have some here. These are in your book. Any sum or product. You could do projections. So you have to think 205 or 255. How many 255? Two of you? Okay, it's the same material. One's just lots of tech labs and those kind of things. The other one is it's the same material though at the end of the day. So it's multidimensional. So you could project onto one axis. So you could say, look, I just want the number that's rolled on die number 1. I just want the number rolled on die number 2. Or I could have the sum of the numbers, or I could have the product of the numbers. So what about this one? Can I have that is exactly equal to this ordered pair? It's got to be a real value number. It doesn't satisfy the definition in the book of being a random variable. Random variables are input or an element from the sample space. Output has to be a real number. So that's no. That would be a nice kind of test question, right? Put stuff there that you can't do and ask you if can I do this? So no, the answer is that it's a real, y's got to be a real valued function. So always back to the definition. The answer would be no. So you don't have to write these down. I just want to have the 3 key definitions that you'll need in this section. There's a lot of stuff in between this, so instead of me pouring out on the PowerPoint a bunch of definitions and you copying it, which is directly from your book, I'm just going to highlight 3 of them. The first one is the definition of a joint or bivariate probability function for y1 and y2. So you could have 2 random variables on the same sample space. And they give some experimental data where they talk about why you might want more than one random variable on that sample space as an application. So it's given by, this little p now is not just a function of y, it's a function of 2 coordinates. Y1 is equal to y1 and y2 is equal to little y2, where y1 and y2 are real numbers from minus infinity to infinity. So it's a multivariable definition of a probability function. So your probability function from before has now two variables. So that's why you're going back to 205, it's vectors. Okay, so the second definition is that how do you get from the probability, you have two things that are always important, the probability distribution function, the probability density function, and the cumulative distribution function. Those are the two things. So how do you go from one to the other? Well, this is the formal definition of a distribution function where you have two variables. It's defined as the this is what you use to calculate your probabilities. And over here, you have the matching that you had with the relationship with the fundamental theorem of calculus, relating the distribution function back to the probability density function. So everything scales, except something's a little bit different in my definition 5.3. If you really, really like 205, you can answer it. And if you really, really hated 205, you can answer it. What's different here? What's different from the previous definitions we had with that relationship? I believe that in your previous definition they put this together as a derivative, right? Later on, and they related this. The second thing is you have a double integral. Remember that? What's that? Improper double integrals. So if you take the actuarial exam, that's what they are. That's what it's all full of, is this kind of stuff. So just to reiterate, that function is called the joint probability distribution function. Your next homework's already out. It's a little bit more computational, but reading through the verbiage, just go back and look at it. That's what it means.
Ma'am, did you mean
Density.
Okay.
No, it's density. I got it right. Yeah.
You said distributions.
Yeah, it's Monday. Okay, so I'm going to show you just a dry example. I'm going to do a few more things. So far, I haven't walked into Dr. Hamatka's class by accident, but I'm going to probably do a few more mishaps today. So I'm going to give you a dry example of how to do one of these computational, how to run through one of these computations, and then I'm going to do another example where it's a homework problem. Oh, actually, this is the homework problem. So if you have a joint PDF, actually I want to end this because I think that the other